So I'll be talking about K decompositions today. How's my voice now? Good. Okay. So keep bugging me if my handwriting is not visible, clear, or my voice is low. So I have tried my best to show you guys that this is a very simple concept, and this is indeed has many connection to some things that we are already familiar with. So I'll try to do that for the lecture. Alright, so before getting into the details, let us review some of the stuff that we already did in the previous sessions. So it was in session 1, Chris went through this list of classification of simple Lie groups, and we had so basically Lie groups, we discussed the matrix groups, and Chris promised us that they are the same. And so we have SL and C, and all of these S would just mean that the determinant is 1. And we had the SL and C, SO with odd and even dimensions, separate, and then SP, U, and C, and all of the real forms. So, and then there was this very weird fifth family which had 5 exceptions, which even Chris couldn't tell us more about, so I'm not even going to try. So now, given these complex forms, you remember how we take its real forms. We had to define some kind of transformation called the conjugation, right? So let me first define what a conjugation is. I won't be able to reach much higher, so I always concentrate on the lower side of. So definition. Let G, H. So G to denote a group, and G and H, small g and H, are elements of that group. Then so I've seen different ways of denoting it, but I would like to continue what we were using in the notation that we used. So G sign, I'll write out this in conjugation. I've seen this be written as theta of the Lie algebra also, but I will stick to this. Is a conjugation if means that if we do it twice, we get back the element, and also that you do it on a product of G and H, you should get back G. So one thing I want you to all note is that the simple dagger operation is not a conjugation in this sense. That's why you have seen in previous sessions that you always take a minus dagger to make this work. Right. And we get the real forms by having some kind of constraint that so real forms are obtained by putting some constraint like so different styles. We have seen that can be transpose, it can involve the matrix omega. We have seen different kinds of now with this in mind, I want to review something that we are all familiar with, that is complex numbers. Right? We can just rewrite some more things that we know in a different way that might be helpful later on. Right, so complex numbers. So complex numbers, which is denoted by C, this is actually can be written as either r plus I r or e to the r so in this form, if C is an element of C, complex numbers, then we know we can write this as R e to the I. Right. So this is what we call a polar decomposition, right? So, so I would like to write this in a slightly different order. It doesn't matter here because it commutes, but I want to write this here. Now we can define a conjugation, which we call conjugation in this case, which has this property. So this star is nothing but r e to the minus I phi. And one way to obtain, and so this is a polar decomposition of Z, and one way to obtain what R is to do this transformation Z that goes to Z star, which is equal to right. So given a Z, if we want to write down in this form, we need to find what R and phi are. So to get R, this is a transformation. Given or defining a conjugation will let us do this transformation, which gives you something like an R square. But now we need to find R, right? So what you should do is to find what is the square root of that. And we have before point about how to choose the square root. Should we choose the plus or the minus? So if you choose the plus square root, we get we can think of this as an image. So we do not include the 0. So we choose the positive side. So in the real line where you remove 0, we had a line to the backward as well. But if you choose the positive square root, we get this. And so increasing R, this means it takes us along this line. And the purpose of e to the I phi is to start with this and then lets us obtain every complex numbers. So you choose an R and e to the I phi kind of lets you rotate to obtain new elements of the group. And notice that e to the I phi is nothing but e to the I phi is an element of U1. So yeah, I won't go into details other than this because okay, so keep this in mind, and when we talk about general KK decomposition, we can sort of see the similarities. It's not all the way there, but there are some similarities that we can. So just want to review that for you guys. All right. So
Gopi.
yeah.
The idea is that like the real forms of C are R and U1.
So one way to obtain U1 is to take something like minus star as the conjugation. So e to the I phi, you conjugate it and you take the inverse, you get back e to the I phi. So that's the conjugation to obtain the real form as U1.
So you choose the conjugation to give you.
So yeah, you know that these complex algebras can have more than one real form. So you can choose a conjugation and that gives you a real form. So now this is one decomposition that you are already familiar with, polar decomposition. But there are other decompositions that I will write in a language that we are all familiar with. So one is this singular value decomposition. Then we have the polar decomposition. And spectral. So, the standard singular value decomposition that how to write a matrix in terms of unitary and a Hermitian part. No, sorry, unitary, the diagonal entries, and so write that U. Spectral decomposition would mean that Hermitian matrices can be diagonalized by unitary matrices, and polar decomposition is something like.
Don't relax.
Okay. So,
Sorry, that was code.
So-
His steady state is smaller and smaller, so he's relaxing to steady
Yeah,
state.
the indices and the exponentials are.
right, so once again, singular value decomposition, you know that matrix can be written as u e to the delta v, but this is diagonal. Spectral decomposition, you know that any Hermitian matrix can be diagonalized by unitaries. And polar decomposition, you know that you can write a matrix as u times e to the t, where u is unitary and this is the Hermitian part. Right, so we will see the generalization of each of these in, so we can obtain decomposition similar to these from the general KK decomposition, so we will see that. Alright, so now let's start. There are different ways of languages in different literature that I looked at, so let me know if you like me to use one versus other or something. But anyway, I'll put up these references, I'll send it to you and you can upload it and you can see that. So, right, so now we can talk about something called a Cartan decomposition of an algebra. Okay? So I'll start with the algebra, not the group. So I'll talk to you about how we can decompose an algebra first. So Cartan so I'll start by defining things and then we can see what each of those means. So let G be finite. Semi simple the algebra.
Okay, maybe I missed this when I was here. What's the difference between semi-simple and simple?
Just that you can form those from simple, yeah, right? By either direct sum or a product.
So SU2 plus SU2 is not simple, it's semi-simple.
I see, so it's kind of like irreducible for algebras? In a sense, okay. I won't distract. I missed class. I didn't read the notes.
Yeah, basically you have these basic building blocks as the simple groups, and then you can develop other semi-simple groups from simple groups.
But not all groups can have simple groups.
I see.
So a decomposition of the vector space in Lie algebra. Suppose we write this as K plus P. This decomposition is called so we'll restate that. So let G be a finite dimensional semi-simple Lie algebra. Then you can decompose the vector space in any way you want. But let this be one such decomposition. Then this is called a Cartan decomposition if this thing holds. What is this? So you have K. So you have two different vector spaces K and P. Now you pick elements from K and commute among themselves. So you find the commutator between elements from K. That's the meaning of this. Then what you get is an element in K, which means that this is a subalgebra of the Lie algebra. Right? Is that clear? So I'm just writing this as the set as such. So if you pick elements from K, commute it with elements from K, you get an element in K. That's the meaning of this. Now, what does this mean? You pick an element in K, you pick an element in P, commute them, you get an element in P. Again, you pick an element in P, you pick an element in P, you commute them, you get an element in K. So this specific commutator relation is a heart of Cartan decomposition. Right? So when we do examples, it will be more clear. Now, along with this, I will define what is called Cartan involution. So,
A real quick question before you.
yeah.
First, I was going to ask, for any semi-simple Lie algebra, can I do a Cartan decomposition? Is this something I can always do?
Yes.
Always exists. Okay.
There is an exact finite number of such things you can.
Okay. And so it's not necessarily unique. Is there, or is it unique?
So they're unique up to choice basis,
Okay.
and there's still going to be a certain number of distinct Ks for
Okay.
every G.
So, Cartan involution is also a conjugation. It's similar. So it just means that you have a transformation that if you do it twice, you get back the element. So, in the notes I have written in a different notation, but I try to use the same thing as before. So Cartan involution is also a conjugation. So these two properties exist. So these were the two things that we saw earlier. Now, if you look at this as, you can think of it as a function that applied twice, you get back the same thing. So now you know that such functions can have plus or minus eigenvalues, because it's like theta square is equal to 1. So you can have plus or minus eigenvalues, and these k and p, if they are Cartan decomposition, those are precisely the +1 eigenspace and the -1 eigenspace of such a Cartan involution. So what does that mean? So
Here, G, H are elements to be copied and elements to
Wait,
be inverted.
Gopi,
yeah.
Gopi,
1 second.
so you lost me there. So that is just the same thing you wrote for conjugation earlier, right?
Right. So there is one more condition for.
Oh, okay.
I mean, yeah. So now, if this is true, which means that G is in the +1 eigenspace of the involution or the conjugation, then this implies that G is an element of K. And if this is true, if this is in the -1 subspace of the involution, then
I'm afraid there's been some confusion, because we probably should be talking about how pi interacts with conjugates and condition.
Right.
Yeah, that's why,
okay.
that's why I got confused, because when we're talking about the multiplication,
right.
are we talking about
Okay. Yeah.
the V bracket versus the, yeah, that's why I got confused. That makes-
Yeah. So the main point is this. So these two, when it's the same thing as a conjugation when applied to the algebra, and since it is an involution, which means when you do it twice, you get back the same thing. It will have +1 and -1 eigenspace, and the +1 eigenspace is such that it is in K, and -1 eigenspace is such that it's in P. And so these were two conditions for Cartan decomposition, right? One, if it has these computational relation, it is Cartan decomposition, and if it is an element of the +1 and -1 eigenspace, it is also a Cartan decomposition. So this goes both ways. So you can define a Cartan decomposition using either of these. So you can find two subspaces such that this commutation relations hold. It will give you a Cartan decomposition. Or you can find an involution and look for its +1 and -1 eigenspace. That will also give you a Cartan decomposition.
You mean to say that if I do the top thing, that there exists an involution, a Cartan involution such that.
And I haven't written it down, but I think I can try one way. So let's just see what happens if I do the conjugation of this. Let's try that. So let me just, so we have G and H, which is an element of K, right? So we want to see, given this, can I get this computation relation? Okay. So G comma H, we want to see whether it is in K or P. I want to just show that. So we can show that by doing this, right? What is this? This is nothing but G I H, right? But each of these are in K, so they are in +1 eigenspace of the involution. So this is nothing but G comma H, right? So G comma H chi is equal to G comma H, which means that G comma H is also in +1 eigenspace of chi. So this is an element of K. Right? And so similarly I can show the other two, which just boils down to the fact that commutation is like a multiplication. We have +1 and -1, right? +1 times +1 is +1. +1 times -1 is -1. -1 times -1 is +1. Right? So it just generalizes from this. And that is because of this fact. Because this is true for involution.
Sorry, so Gopi, so one thing that you said that I maybe missed a little bit was, were you saying that if you give me some semi-simple algebra and I find a conjugation, I can figure out what these eigenvalues are, or sorry, these eigenvectors of this, or I guess
Eigenspace.
elements of the algebra. Yeah, figure out the eigenspaces, and then that tells me how to do the Cartman decomposition.
Right.
Is that the
And-
idea? Okay.
Yeah, and it's not unique.
Yeah.
I mean, you can find another conjugation.
Yeah,
that
yeah.
can be used.
Nice.
So yeah, another point that I was also trying to make is these two are equivalent. So you can either find K and P such that these commutative relations exist, that will give you a Cartman decomposition, or you can find, you can choose an involution and then look for its +1 and -1 eigenspaces. That will also give you, or as Ivan was pointing out, if there exists K and P such that these commutative relations are true, then there should exist an involution of which K is a +1 eigenspace and P is a -1 eigenspace. I might be able to prove it, but I don't want to try that now. I haven't. Alright, so finally we come to the title of the talk, KK decomposition. And in the literature that I was following, the language is like, we called Cartman decomposition for the algebra and KK decomposition for the group. And if that is universally accepted or it's just that others remember it. Right, so next one is the KK decomposition of a Lie group. So right, so the theorem that tells you such a decomposition exists is called Cartman decomposition theorem. So I'll switch that. So let G be a Lie algebra with Cartman decomposition the way we defined just now. Then the elements of the group defined or built from the Lie algebra can be written as now G is an element of the group. The theorem says G can be written as K e to the delta Q, where K comma Q is in e to the K. So that's a group generated by the K subspace of the algebra, and in script A. Alright, so I didn't define what this is. Okay, so just give me a couple of minutes to define that. So zooming on this commutation relation. So any element in P commuted with any element P goes to K. And now, so P is not closed under commutation, right? But I want to find a sub-algebra within P. How do I do that? So a sub-algebra would mean that if we choose two elements from that algebra, their commutation should also be in that algebra, right? But any such element, the commutation is going to be in K. So the only possible sub-algebra is an abelian one, because their commutation has to be the identity. Because identity is the only element that is both in K and P, right? Or 0. Right? So that would mean that if you want to find a sub-algebra, the only thing that is an abelian group. And now find the maximally abelian group. So construct all the elements that commute with each other. That is A. So A is the maximally abelian group of P. Or we can think of it in different way, that written in that basis, this would be diagonal. Right? Written in the basis of A, this would be diagonal. Because they commute with each other, so you can find common eigenvectors. If you write in that basis, this becomes diagonal. Right?
Okay. You say A is the group generated by this maximally sub-algebra?
A is the algebra. Yeah. And E to the delta is. So,
can you repeat what's diagonal in what cases?
so I was just trying to say the same thing in a different way. I know that is fully correct, but what I was trying to say is that since all the elements in A commute with each other, you can find mutually or common eigenvectors for them. And written in those eigenvector basis, this would look diagonal. Thank you. And so this, as you see it, is also a generalization of singular value decomposition. You can sort of see that. But the way we define singular value decomposition only works for, I mean, the standard one is for a specific groups and stuff that we'll look at later. But this is of that form. So this is literally K, A, K decomposition, where K, these two elements come from K, and this comes from K. So that's a K, A, K decomposition. Alright.
Why is it important that they were, and maybe we'll see that, the plus one, that if they're from K and not from P, on the path, P, A,
So this
P.
is from P.
Yeah, so that's from, oh, that's because that's from P, but it's the abelian part.
Yeah.
And then the rest of it's from K.
Again, I won't try to prove this in this lecture because I myself
Yeah.
haven't.
I mean, you know, it's just my way, my damn physics. I mean, I find there's all these definitions, but why is this like this one? Or where did this, how this has come from? I mean, why this, not anything else? We'll see, maybe.
So, if I might
Yeah.
comment a little on that. So if you look at the middle commutation relation,
Yes.
anything on K equals P, then what that means is when you conjugate by the subgroup K, that moves you around P.
Okay.
So it's almost a spectral theorem, right? Because you're thinking about Hamiltonians that are conjugate to each other.
Okay. Yeah,
It's basically already there.
I see.
That proof.
I see. So K is a kind of more powerful
Yeah, it's more
sort
specific.
of sub-algebra than P in a sense. All right. That helps.
Sorry, so I'm still a little confused about A. So A was coming from the fact that P only has trivial subalgebra.
Abelian.
Abelian subalgebra? What does it mean for a subalgebra to be? Oh, just things that commute to get the identity? That's the idea? Okay.
P gives 0.
Okay.
But they're not zero, so they're not true.
Yeah. Either the P's
Yeah.
are abelian.
Yeah. Okay.
Or either,
So those guys
either
are
the
abelian.
Right.
But is this still going to, so, sorry, I'm just trying to reconcile this with like the statements that we had in the lecture that I gave about simple Lie algebras only having discrete abelian normal subgroups.
And P is not an
Abelian.
algebra.
Yeah.
Huh?
P is not an algebra.
P is not closed under
Yeah, P's not
conjugation.
okay.
Yeah,
Yeah, okay,
it's not in P, right?
okay,
But K is a subalgebra,
yeah,
but P itself is not an algebra.
okay.
P's a subspace.
Yeah. P is just whatever is left after getting the K.
Okay.
So A is a subspace of P
Mm-hmm.
that is closed in itself. But if you brought K in, oh god, the commutators are crazy.
Okay.
Could we quickly throw in maybe just one example so that people can
Yeah, I have a lot of examples, but there is one thing that I thought I would say, but this want me not to, but I'll tell anyway. So I also would like to think of the complex numbers in this way. At least one point where we both agree that e to the delta, you can think of it as the radial part, which means that there is this direction, abelian direction, where you can, so these are the singular values, right? This delta gives you the singular value. That determine how far from the origin you are, right? And then this e to the I phi or ks will rotate you from that abelian group to other members of the group, other elements of the group. So this singular values determine kind of the radial part of it, and then you use these to move away from.
Is that why they're called singular values? It's not far away from the singularity.
Yeah. It has a singularity that they can zero.
I wonder why it's called the singular value decomposition, that's why.
I never knew.
There's like a more general idea of singularity, right?
Yeah, beyond the complex numbers, you have more general things.
Yeah.
And if you look it up on Wikipedia, singular value decompositions have been independently rediscovered this decade, that decade. Certainly geometers are the ones who pointed it.
And if you want to think about this example yourself or tell it to others, please contact us before you do that. Then there are many subtleties that you wouldn't want me to misuse. Okay. Right. So this we have established that this is similar to the singular value decomposition, but we still have two other notions of decomposition that we are familiar with. So how does that come about, right? So there's a polar decomposition and the spectral theorem or spectral decomposition. So right. I'm just wondering which one to do first. So I'll do the spectral decomposition in this case. So the spectral theorem that is associated with it, the Cartan decomposition theorem, says that if, so this is the spectral theorem in this case, it is much more general than decomposition and unitary stuff that we are familiar with. So this says that if G is an element of P or P, so P is the group associated with the what's this? P? It's not a group. Yeah. Whatever. This e to the p. So if this is the case, then we can write G as k e to the delta a inverse. So which tells you that a general element can be written in this way as singular value decomposition. But if that element is in P, then you can diagonalize it using elements in K. So always have in the back of your mind what the spectral decomposition that we are familiar with. We have Hermitian matrices and unitary. So remember that unitaries are generated by anti-Hermitian operators. We're not familiar with that language, but it's always e to the IH, right? So we have anti-Hermitian matrices and Hermitian matrices. This forms a Cartan decomposition. Okay? I'll get to that and we can talk in detail, but just to have that in the back of your mind. So IH or e to the IH is like K here, which is the special unitary group. And then you have Hermitian matrices, which is in P. So what this tells you is that if you have a Hermitian matrix, you can diagonalize it using unitaries. So K, so you can diagonalize any element in P using an element in K. Okay? Right. So can I erase that stuff? Right, so, yeah.
When you make this decomposition, the Hermitian, the anti-Hermitian matrices, what's the full Lie algebra?
The SL, NC. So, any special linear, so that's just every matrices that has determinant bond, right? So you can always write it as Hermitian plus an anti-Hermitian matrix. So you can divide it into Hermitian and anti-Hermitian. Because the algebra SL would mean that they have traceless. Right. Right. So now what we have is the Pollard decomposition. So we can start with this. So any element in G, we know that we can write it as K e to the delta Q. This is what we learned as the K decomposition. So now what you can do is you can write this as some K prime Q inverse e to the delta Q. You can always write that. Thus that K prime Q inverse is K. Okay. But because of the commutation relations, and we have already seen this, Q inverse e to the delta Q is an element in P. Okay. So this is equal to K prime P. Is that notation okay? So this is a familiar form of polar decomposition. So now again we can think of it as a Hermitian anti-Hermitian. So what is this part? K is the group generated by the anti-Hermitian, which is the unitary, and P are Hermitian matrices, positive, semi-definite. So you can actually, that's just so you can remove the negativity into the unitary, right?
I think either Hermitian is just one.
Yeah, yeah. So K prime in that case comes from the unitary group, and P are all Hermitian, positive, semi-definite Hermitian matrices. So any matrix can be written as unitary multiplied by a positive semi-differential measurement. That's a polar decomposition that we know, right? So this is a generalization of that. And okay, any questions? All right. Just before moving to the next, listing down different KK decomposition. Even though I won't try to prove this. We can see how to find what K and Q are. So how do I construct a decomposition once we know that this exists? That's the next task. So now remember how we found out what R was from the complex numbers? So you had this transformation that it takes you from Z to mod C square or Z times C star, right? So we will do something similar here. So first we'll write down what this is. So chi is a Cartan involution. Remember that in the algebra we have plus and minus 1. So in the group, so just keep that in mind. So K is invariant under that, so we just have K. And delta is in the algebra, which is in P, which will get a minus sign. So this becomes e to the minus delta. So once again, if you are doing the Cartan involution on this G, we know that, let me just write steps down. So first, we delta Q, right? But we know you can apply that on the each of them. So K I e to the delta I. But these two come from the subgroup K, which are invariant under that Cartan involution. So they remain the same. And delta comes from P, which has a -1 value. So delta becomes minus delta, and this becomes its inverse. Right. Now, let's find out what is this, the inverse of this. So this is also denoted by G minus chi. So what's the inverse of this? Q comes here, Q inverse, e to the delta, K inverse, right? So this object right here, G chi inverse, is something similar to the conjugation in the case of complex numbers. Why? We'll see that right now. So what did we do that earlier? We did Z times Z star. So we'll do something similar. We'll find what is G minus chi. G multiplies by this. So Q and Q inverse goes away. We get this, right? And reverse. So now what you have to do is to diagonalize these two matrices and take the square root of that. So again, we have a choice of what square root to take. So this is similar to the fact, when you have singular value decomposition, you take things like transpose or things like that, or dagger, and find what is positive Hermitian part of that, and then find what the unit is. Right, so if you solve these two, you get Q delta and K. So this is the construction or substitute way of finding what the decomposition is.
If I could make a comment.
Okay.
So you would diagonalize this matrix like you would any other. So you can consider this theorem of promise that your eigenvectors and eigenvalues will have more structure than you might have expected, just diagonalizing a generic matrix. So don't forget that, you would diagonalize GG just like you would any matrix. suddenly be surprised that you have these degeneracies and all kinds of really things happening.
What is our structure? I would see that, I would be surprised to see in this case.
Because this isn't any positive permission matrix, it's something that's E to the P. And so the spectrum is going to be more structured.
I see.
Right. So now we have seen the A decomposition in 3 different ways. The one that we are familiar with as singular value decomposition, the polar decomposition, and the spectral theorem that we have seen also. And I think I should note that all 3 of these come hand in hand. When one exists, we can find all 3. And I kind of showed you how to go from one to the other. I'd like to pause here and ask if there's any questions. Okay, so there are like 5-6 pages left, I think. I'll try to see how much I can finish. Okay, so the rest of the lecture would be in the following way. So there is a specific classification of every decomposition that you can find, and I'll go through them one by one, and whenever there is an example that we can see that we are familiar with, we can expand on that or zoom in on that and then discuss that. And if I'm running out of time, I think I'll just pick up all the examples and just explain that. Okay. And you can read my notes later to see what the other classifications are. Alright, so there are 4 types. It's very clever to call them as type 1, type 2, type 3, and type 4. So we have 4 of them. I'll start not in this order, but I'll start with 4 and tell you what they are. So we have already discussed the classification that I just reviewed in one sentence in the beginning. We have these 4 different SLNC, SONC, SP2NC, where this was further divided into odd or even, right? So given any complex Lie algebra or group of this form, we can find a unique, maximally compact real form. Don't ask me how I get that, but that's a fact. Which means that there is a real form that is maximally compact. It's a subgroup of these. For SLNC, that is SUN. For SONC, SON. And for this is SP2N. So these are the 4, by considering this as both odd and even. So 4 types that comes under type 4 K decomposition. So in this, I would zoom in on this SLNC in top. So we have SUN, this subgroup of SLNC, NC. So the algebra SL and C is actually plus I n, where this are the anti-Hermitian matrices and denoted by IH, and these are the Hermitian part. So we would like to show that this is a Cartan decomposition, right? So we got a subgroup in SL. So this is a subalgebra, small SU. We want to show that this is a Cartan decomposition. So one way to show is to show all those commutational relations. So what we can show is IH comma IH prime. You can see this. So we know that when you do this, whenever you take the commutation between two Hermitian matrices, you get an anti-Hermitian matrix. Because of the fact that you take the dagger, you flip them and get a minus sign. So because we have an I there, so we get this is anti-Hermitian operator. Now I find what is this. So this is an element from, so I can probably write, we're going to do all this, K and that P. Okay. So K is of algebra, whichever is closed or which has this nice forms. P is whatever is the rest of it. So this is showing that K comma K is K. Now K comma P is actually I H prime. This is actually H prime. So I get a 9 from here, and then you get a Hermitian matrix. So this shows that K comma P is in P. Right? And now we have H prime is I. Right? So this is P comma P is in K. So we have shown that this is indeed a Cartan decomposition. So what is the, so we know that if a Cartan decomposition is there, we should be able to find a Cartan involution or a conjugation. So what would be the conjugation that is best for this? Can anyone suggest me one? So K should be in the +1 eigenspace and P should be in the -1 eigenspace of that. Yeah, dagger would almost work, but it just switches. So we just put a minus sign. Okay. So if X is in SL and P, X G chi is nothing but minus G dagger. So if we have anti-Hermitian operators, by doing the dagger, you get a minus sign, and you cancel that with this minus sign. So you get a +1 in space, and then Hermitian would get an extra minus sign. So this is the Cartan involution that also has the same properties, and will show you that this is a Cartan decomposition, right? And
So, a quick comment. So those other two type 4s, they split up under this exact same conjugation. Still chi is -10.
yeah, this. Right. So in this Cartan decomposition, we can just, we already discussed this, but we can rewrite what the different decompositions would give us for the group. So the K decomposition in this case would tell you that any matrix M in SLNC, capital SLNC, So what we have studied from the K decomposition is that M can be written as K e to the delta Q, right? So in this case, K is generated by the anti-Hermitian, which is the unity group. So what it tells you is that M is nothing but U e to the delta V, where delta is Hermitian, or e to the delta. It's a diagonal entry, and this is Hermitian. This is the KK. Now we can look for what does the polar decomposition give you. So it tells you that any element M can be written as an element in K, which is a unitary matrix, and an element in here P. So e to the B is a Hermitian operator, positive semi-definite, and U is a unity. This is the polar decomposition that we know. And third, if H is in P, or P is e to the script P, then we know that H can be written as U any Hermitian operator can be diagonalized by unitaries. So that's the spectral theorem associated with the Cartan theorem. So once again, these standard decompositions came from the fact that SUN or SLNC mod SUN is a symmetric space. So this is a term that we use for this. So these two are called a Cartan pair, and these two are called a symmetric pair. So whenever you see the name symmetric pair, it just means that you have a bigger group, a smaller group, and the smaller group and its complement forms a Cartan decomposition. So you have a bigger group, a smaller subgroup. If they form a Cartan decomposition, you call them symmetric pair.
Okay, I missed the point of when you said that these groups were the natural compact groups.
Yeah.
What the heck does that have to do with anything?
I mean, so first of all, you just need to find a subgroup,
Right.
So this, and we are trying to classify them to different types,
Okay.
right? And you can have more than one decomposition associated with one bigger group. But this is the one that we get by doing that. I don't know how you get that, but it's a fact that any complex D group has one and only one maximally compact real form, and they also form a Cartan decomposition.
So there's some relation to that, this real form and the Cartan.
Because so I don't know if every real form would make a Cartan decomposition, but the way you get to a real form is by introducing a conjugation and stating that G conjugate should be G. That's how you get the real forms. The same conjugation would work as the involution. So is that true, Chris? Any real forms can be made into a Cartan decomposition?
Yes, with the one subtlety that maybe you're aware you can't take squeeze generated and conjugate it into something that acts like a number operator. Maybe that's because, e to the I.
That's true, yeah, that what does that have to do with this? I can't make that.
Yeah, I guess I'm asking you to believe that. Right?
Okay,
That it's
yeah.
precisely when you're thinking about compact K
I see.
that you don't have this funky
I see.
discrepancy
I see.
between different kinds
So the
of
fact that
elements.
it's compact is
Yes.
It can
Yeah.
connect everything with E.
So you need a compact real form, and this type 4 contains all such compact real forms which are maximally compact. There's just one classifying parameter.
But if you don't have compact real form, you can in fact do similar decompositions like that in
And I'll just mention some of the things that we know about these. So you have SONC and SON. So in here K is SON, right? So what we know is that so this is generated by antisymmetric matrices, right? So the spectral theorem, I don't know about the other ones, but at least I can say about spectral theorem, would say that every symmetric matrix, which is the P in that case, can be diagonalized by rotations, SO, orthogonal matrices. So every symmetric matrices can be diagonalized by orthogonal matrices. So that is the spectral theorem associated with this Cartan decomposition. And I think this talks about antisymmetric matrices.
So I don't think what you said is quite right, because here SON is real antisymmetric, and then SONC is real and antisymmetric. So I think you're confusing the like the vectors, which also have the necessary.
Okay. Then never mind. So is this also SON plus I? SON. So oh, you're doing a transpose and not a dagger, so
Right.
both are antisymmetric.
Yeah.
Sorry about that. All right. So these are the 4 ones in the type 4. So I'll just start with type 2, and I really think that you can read these classifications in my notes, and we should just discuss some of the examples that we know. Right? I mean, I already discussed 2 of them, but we can look at if we can do some more. So, so now we can discuss the type 2. So we have now discussed how to get a Cartan decomposition by taking the maximally compact subgroup of the complex form. That's what we did. So if we have SL and C, we had SU N. So this was type 4. Right? We just discussed this now by using this conjugation relation minus dagger, right? And so another real form that we can think of is SLNR, where the conjugation is just the conjugation that we know. So now, since this is maximally compact, I can find a group that's the intersection of both of these. It's again compact, and both of these conjugation would work. So we can find SL and R intersection SUN, which is actually SON. These are real matrices. These are unitaries, so we get orthogonal matrices. Because this has the thing that dagger is its inverse, right? But it has to be real. So this boils down to saying that transpose is inverse. So the intersection is something what SO. So we have this. So, so the good thing about this is that we can use the same conjugation that we use here and apply it to this, and see what happens if you do this. But again, we know that this is already invariant under taking the star or conjugation, so I can just replace this diagonal with the transpose. Right. So this right here is a type 2 Cartan decomposition. So because you can see that when you take transpose and negative and inverse of that, you get back an orthogonal matrix. So given an orthogonal matrix, you take the transpose and take the inverse, you get back the. So this is in the +1 eigenspace of so basically type 2 decompositions we can obtain from taking a real form. So first you take the maximally compact real form which you have defined. So you have SUN, SON and SP2N. So you have that. Then you can take any other real forms, right? And then take their intersection. So you get a compact subgroup of this. And you can, so because it's the intersection of these, this is invariant under both of these conjugations. Okay? So, I mean, we have already seen that this is invariant under this. So there's no point in using this again because both of these are invariant under that. Use this conjugation on this. That's how you obtain type 2 Cartan decomposition. This is the way they classify different things.
So we've always got like a square diagram like this. It's just, we're just swapping what the corners are. And what those. You maybe probably put the negative dagger one on that side. You could put something else over there, and type 2 would be the thing that appears on the vertical line to the left.
Right. And I guess this was type 4. This was the one we initially discussed.
So this type 1 is the one that says symmetric matrices and diagonalized by rotation.
The dual.
Yeah, SLNR contains also.
Right. Because any real matrices is antisymmetric and symmetric. Right. Yeah. So just to repeat that, this is any real matrices, and these are orthogonal matrices, which are generated by antisymmetric matrices. So the spectral theorem would tell you that any symmetric matrix can be diagonalized by orthogonal matrices. This is the theorem that we already know. Okay. So you can just look at one more example from here. So I can show you how we obtain that too. So another one that you can look at, let's see. So this is another just type 2 decomposition that we can do. So you start with SP2NC, which is a complex form. You take its maximally compact integral, which is SP2N. You take another real form, SP2NR, and take its intersection UN. The reason why I'm specifying this is because we are familiar with this, where n would denote the number of bosonic modes. So what these denotes is that sp 2 and r, you can write that in terms of, we can do like that x is something like q1, q2, so different modes q and p, q1, q2, we define them in this way, right? Then we can write any quadratic Hamiltonians, so any Hamiltonians as I times some matrix so this is all quadratic Hamiltonians in bosons. Yeah.
What is H?
Mu nu. That's not visible. Right, and so in this case, we have both number preserving and spacers. So, like the operators of the form A, dagger A. Then we have A dagger, A square plus A dagger square. So this is for one mode, but you can think of the generalization of that. And you have the spacing. So in this, if you only concentrate on the number preserving part, so in general case you can have AI dagger AJ, and which preserves the number of excitations, then that forms U of n. So here the number preserving one is an element of U of n.
What's the difference between SP2N and SP2N comma R?
So SP2NR is same as SP2N3, but with they are real. S star is equal to C. And then SP2N, the conjugation is with that omega. So omega, Palermo characteristic is omega M inverse dagger, omega inverse is
SP2N is a compact part of SP2NR.
So all of its squeezes at the engineering.
SP2 and R is unusual thing for Gaussian stuff. SP2 and C expands that with like even left raised in one I times the emission stuff in our language. And then going down to SP2N would be like photon mobility stuff unitary, but then I made the squeezes anti-unitary.
So in this, it would say that every squeezing operations can be diagonalized by number preserving. That's the block Messiah decomposition. I'm guessing Tyler, you'll be talking about this next week. So yeah, more about this next week.
Sorry, Gopi, could you write down what the two conjugations that define the real forms sp2n comma r and sp2nr real quick? Because I just want to see that that conjugation gives you exactly the conjugation that gives you un.
Help me.
Is that going to be true?
This is
It's the same two concepts.
Yeah, you just
and this is omega.
Oh, no, that one's also interesting.
Oh, right.
oh, it's just inverse dagger. Oh, and then it just gives you transpose. Inverse
Oh,
transpose.
this
Wow.
is this already has that
Yeah.
omega thing in it. So
Alright,
once,
yeah.
once you have that restriction, then
Great.
it's the same thing.
Alright, yeah.
But if you're doing things in quadratic boson operators, the conjugation is actually the Fourier transform.
So these are not literally 2n by 2n matrices. Like they transform as if they were.
Sorry, you're doing things with quadratic boson operators. That's not everything that's up there? I mean, which thing are you pointing at whenever you say we're doing things with?
So Gopi wrote like A's,
Yeah,
and
yeah, yeah.
X's, and Q's and P's.
Yeah, yeah.
And those are not 2n by 2n matrices.
Oh, okay.
But they all have commutation relations that are the same as if you had just converted their 2n by 2n
Oh, okay.
coefficients.
Yeah, yeah.
In which case it doesn't make sense to apply these conjugations to those Hamiltonians. But the conjugation you perform that does the same thing as inverse standard is the Fourier transform.
Okay.
But if you just wanted to work in boson,
But if you think about x and t's,
yeah.
Probably get into subtlety.
yeah. Entirely will
right.
explain all of that in the future, actually. Yeah, you could. Yeah. All right. So I guess at this point I'll just take one or two examples from. So we have type 1 and 3 left. I'll take one example from each and then maybe stop there. You can look at my notes for.
Oh wait.
Oh.
You have one waiting for you right
Oh.
there. You're gonna have it, so.
Alright, so I'll just talk about n equal to 2 just so that it's a bit easier and it just carries over to any n. And so the okay. I'll try to explain this, but I haven't fully convinced myself how this works, so forgive me if I leave some parts with and you can explain. So look at SL2C. So these are all the matrices. So we can generate them using stuff like sigma y, sigma z, sigma x, and then there so ix, I sigma y, I sigma z. So this is also the reason why earlier we wrote SL2C is nothing but SU2 plus I SU2, right? Now if we come to SU2, these are generated by the I things or the anti-summation ones, sigma y and z. So you know this is the unitary thing. Now SL2R should be generated by real matrices. So you know the real matrices are I sigma y. So sigma y has an I in it, and if you add another I, it becomes real. And sigma x and sigma z, right? And so if you take the intersection of those, you get that I sigma y. And so here we talked about this is type 4, this was type 2, but this is also a compact subgroup of SU2, right? So we can think of what decomposition does this give us, and this is actually type 1, right? So there is something about 1 being a Riemannian dual of 2, which I'm not completely, I don't understand completely, but it is something like a weak rotation of the generators. So you can think of these have sigma x and sigma z. These have I sigma x and I sigma z. You weak rotate them here and you get type 2 to type 1. So similarly, when I talk about type 3, type 4 and type 3 are duals of each other. But yeah, I don't know how to explain it further than that. But we can zoom in on this and see what this means. So SO2 is whatever that is generated by I sigma y. So let us zoom in on SU2, where so SU2. So with that, I can write this as sigma y plus
Which one do you want to share?
and I can stop here. Yeah, I'll just explain this. I have one more example, but I'll try to write that up in the notes. Okay, so, or I'll just mention one more. I won't take too much time. Okay, so this is what it means by this time decomposition. So you have this subgroup, which is a subalgebra here, and then you have the rest of it. So now, I don't have to go into detail. You can see in your head that this forms a Cartan decomposition. So some of the things, this commutes with itself. So k is in k. There's only one element. K with p is always going to be in p, x, y, z, and z, y, x, and p in p is always in k. Right? So it forms Cartan decomposition. So what does that tell you about the KAK decomposition? Right? So any unitary matrix in SU2 can be written as, so you have k on both sides and p in the middle. Before getting into that, we should see what the maximal, the abelian group is. So if you take both of them, they will commute to something that is not inside that, so it's not closed. So anything smaller than that is just one element, which commutes with itself. So if you only take any one of this, say for example I sigma z, it commutes with itself, so it's an abelian subalgebra, right?
So can you,
Yeah.
is it just the abelian part? Is that a better way to put it? Since it's not necessarily a subalgebra?
It is a subalgebra, right?
I mean, if I take commutative, I thought that was the whole point of what we were saying.
So zero is
Okay.
in all subalgebras, right? So if you have only one element,
Mm-hmm.
it commutes with itself. So sigma z with sigma z is 0.
Okay.
So it is a subalgebra. It
Okay.
does not move you out.
Oh, okay.
E is not a subalgebra.
But A
Some
is.
part of it.
Yeah, sure. Okay.
And it's not a normal, it's not an ideal
Yeah,
case where you have
yeah. Sure. Okay. Yeah, I understand.
I mean, I think no subset of P can be an ideal, right?
right?
Because it always takes you out of the, unless it is ideal. Right, so this is nothing but, you can write it as I y sigma y e to the I e to the z e to the I. I mean, you might have seen this in a slightly different way, but these are nothing but the Euler-Anker decomposition, right? So you have the stuff from P. You can either write sigma c or sigma x, doesn't matter. It always exists. And these two come from K. It's a K decomposition, right? And just to remind everyone what was the Cartan involution in this case, it is just a star inverse, right? So, yeah, you can write that in some basis. In the basis of sigma z, this is true. Because in the basis of sigma z, I sigma y is real. So, no, you know, keep forgetting that you include I in the Hamiltonian. Right. So this is the case, and you can talk about what spectral theorem says. So spectral theorem just tells you that you can diagonalize anything in the equator of or x and z plane with y. In the other language, the x-y plane can be diagonalized by z. Things like that. right? So I want to quickly mention one more thing. So let's find out what that is. Okay, so another type 1 thing is, yeah, we have right here. So I'll just say this. So we have SON is a group of SUN, right? So I just want to mention this because this is something that we are using in our research, me and Chris. So I just wanted to mention that. So think about different generators of SUN. So there are these generalized Gell-Mann matrices that we use to define the generators of SUN. So different Gell-Mann matrices are like this. So there are some stuff that is similar to sigma x. I can write this as L prime plus L prime L. So this is like a sigma x in that subspace. So the states are 1 through n. Okay, and we have these y-type Gell-Mann matrices. Nothing but times I times L prime minus 1 and C. I'll just write this as this, but it's slightly different, but just that way. So what we were trying to do in the case of implementing boson sampling in these optical lattices, so you can think of optical lattices as different sites, and each of them as 1, 2, 3, etc. up to n, and we have these generators. So by manipulating the different hopping amplitudes and the lattice depth, you can change this and this. So if you don't have any phase control, you can change this and this. Although in the lab you can only do a nearest neighbor version of this, but let's just think that we can do everything. So as we have seen Anupam discussing last week, we can think about how that generates the whole any arbitrary unitary transformation by the form of quantum control, right? So we have been thinking about that, and in this case what I want to bring to your notice is that this is a real matrix, or it is forms SON, and the whole thing is SUN. So they also form a Cartan decomposition. So basically the stuff that generated by this and the stuff that is generated by X and C, something very similar to this. It's the same thing that we are talking about. So this carries over to any n. So this is K and these two are P. So what we can look at is that any element in P can be diagonalized by elements in K. So any element in P is what you can do in lab, right? But you can write that as e to the lambda y stuff and e to the delta and e to the lambda y. So this decomposition is something that we use very much in our research. I just want to mention that. Yeah.